we are allowed to add two events together if they're mutually exclusive. We're also allowed to add if they're not mutually exclusive, as long as you subtract what you double counted, right? The overlap. So we're going to learn about the overlap today. The probability of A and B. So remember this symbol here means and, okay? Now, and means like both at the same time. And it also means multiply. Okay, so or means add, and means multiply. You are always allowed to multiply the probability of A times the probability of B given A. Remember that this bar reads given, all right? So this is called the conditional. You're always allowed to multiply by the conditional. So if I said, what's the probability of drawing an ace and an ace in a deck of cards, okay? So the probability of drawing an ace and an ace. And this would be without replacement. Okay? That means that the second event is conditional on the first. So what's the probability of drawing an ace on the first draw? 4 out of 52. So that's the probability of A. Now let's say I don't replace it. You assume you drew an ace. So how many are left? Out of how many cards? 51. So this is legal math right here because I just multiplied by what's called the conditional, meaning I multiplied by getting a second ace, assuming that I got an ace on the first draw, okay? So that is legal. You can always multiply by the conditional. The Pew Internet and American Life Project reported that 79% of teenagers ages 13 to 17 use social media. And 39% of teenagers who use social media feel pressure to post content that will be popular and get lots of comments or likes. Find the probability that a randomly selected teen uses social media and feels pressure to post content that will be popular and get lots of comments or likes. All right, so we have the probability that they use social media and that they feel pressure to post content. They're giving us the exact numbers that we need to multiply. All right, so the first event is the probability that they post social media, which apparently is 79% who post to social media. And then this 39% is the conditional because it says 39% of the teens who use social media feel pressure to post popular content, meaning we know they post to social media. We know that second thing is already happening, or that first event, all right? And so we can just plug in 0.39. Again, they're giving us the conditional. We multiply those together, and we get a 31% chance. Okay. Tree diagrams. Why will this not let me move? There. Oh, good. I need to get that out of the way. Shannon hits the snooze button on her alarm on 60% of school days. If she hits snooze, there's a 70% probability that she makes it to her first class on time. If she doesn't hit the snooze and gets up right away, there's a 90% probability she makes it to class on time. Suppose we select a school day at random and record whether Shannon hits the snooze button and whether she arrives to class on time. Make a tree diagram displaying this chance process. All right, so a tree diagram is used when you have conditional probabilities. I wouldn't write this whole definition down, okay? This is just showing when there's like multiple stages. And basically, you can only use tree diagrams with conditional probabilities, okay? Okay, so these are conditional because, first of all, she either hits the snooze button or she doesn't hit the snooze button. And this is what a tree diagram looks like, okay? We have two outcomes on the first one. She hits the snooze button 60% of the time. So I'm going to put 60% or 0.6, okay? And she hits the snooze button. Which means what percent of the time no snooze? 40% of the time, no snooze. And she gets up right away. Boom, out of bed. I started paying my kid $1 to get out of bed. It was effective. It works. So he gets $1 every day. He gets out of bed, gets dressed, gets ready without any whining, complaining. It's really parenting at its finest. It's been worth it. I mean, it's been worth it. Okay. Your parents are like, just get up. Okay, anyways, that was distraction. Sorry. Okay, if she hits snooze, so we're up here. If she hits snooze, there's a 70% probability she makes it to her first class on time. So these are conditional, so they can go second based on if she hits snooze, then we have something happening, okay? So now we're either on time or late. All right, so if she hits snooze, we've got 70% chance that she's on time. So then what would be her chance of being late? Good. All right, and then we got our no snooze, just gets out of bed, all right? There's a 90% chance she makes it on time. So I've got 90 here, and then I've got on time, which means what percentage she's still late, even if no snooze? 10%. Pick up that pace. All right. So make a tree diagram. We did that. All right. What is the probability that Shannon hits the snooze button and is late for class on a randomly selected day? So the probability she hits snooze and is late for class. Now, the formula that we just learned from multiplying is we do the probability of snooze times the probability of late given snooze. Okay, we're always allowed to multiply by the conditional, and they're giving us these probabilities. What's the probability she hits snooze? 60%. What's probability she's late given she hits snooze? 30. All right, and we multiply those to get our lovely answer. What is the probability that Shannon is late to class on a randomly selected school day? All right, probability that she's late. Now, there are two ways that she could be late. She could hit snooze and be late, or she could no snooze and be late. So we're actually adding together two different multiplication problems, all right, because or means add. So one of the ways we just did, I'm going to go ahead and write that down, 0.6 times 0.3. So that's the pathway where she hits snooze and is late, here to here. Now I've got no snooze, but she still could be late with the no snooze way. So we put a plus sign in the middle between our two options. Everyone's sick at my house. It's great. All right. This was 18%. This guy's 22%. All right. Suppose Shannon is late for class on a randomly chosen school day. What is the probability that she hit the snooze button that morning? All right, this is a conditional statement. I know. So you have to be able to set up this piece that we learned last week, okay? The second thing is what we know happened, and the first is what we're finding the probability of, okay? Suppose that Shannon is late for class. What do we know happened? We know she's late. What is the probability that she hits snooze? Now, we don't have a table. Remember when we have a two-way table, we isolate the row or column. When we have this, we're going to use our formula that's on the yellow sheet that we learned last week, which looks like this: snooze and late divided by the probability of the second thing, which is late. A lot of times, the problems you're going to see, they're all going to lead to one of these, okay? And you probably already did portions of it until you get to this point. So it's really nice. They set it up for you. So we did snooze and late right here, okay? That's the numerator. Divided by, I don't know why I have that extra. Okay, divided by the probability of late was all the pathways to late, which is this 22%. And we divide it. Okay, so if she's late, it's an 82% chance that she hit the snooze button. Okay, given that she's late, what's probably she hit snooze? Pretty likely, all right? All right. We'll try another one. Recently, Harris Interactive reported that 20% of millennials, 25% of Gen Xers, and 21% of baby boomers, and 17% of matures, the really old people, read more ebooks than print books. According to the U.S. Census Bureau, 34% of those 18 and over are millennials, 22% are Gen Xers, 30% are baby boomers, and 14% are matures. Suppose you select one U.S. adult at random and record which generation the person is from and whether or not they read more ebooks or print books. So be careful, the order that they did this one is not in order of the tree diagram. So notice, first they told you who's reading ebooks and print books. Then they broke out the different age groups. We want our age groups first. And then based on the age group is the conditional part, okay? Because it was saying 20% of millennials. So I need to know they're a millennial first before I decide if they're reading an ebook or a printed book, all right? So you're going to set up all your probabilities. This is our generations here, or whatever these are, okay? And then we have ebooks or nope. Ebooks, nope. Ebooks, nope. Okay, and I just found the other probability. They only gave us a 20%, so I had to fill in the 80%. Okay, everyone got it? 25%, you fill in the 75%, because they're telling you of each generation who reads ebooks. All right, so I got my tree diagram. Find the probability that the person reads more ebooks than print books. All right, so that would just be the probability of reading ebooks. Okay, this is all the pathways to ebooks, just like we did all the pathways to late in the last problem. All right, so you could be a millennial who likes ebooks, and we always multiply these together. So one option is we have our millennials who read ebooks. 20% of the millennials read ebooks. Then we have our Gen Xers, there's 22% of them, and 25% read ebooks. So we multiply those together, but we add each pathway, all right? So that's say, I can't read the boomers. What is that, 21? No, we're down here, 30%, all right? So I have 30% are boomers, and 21% of them read ebooks. And then I have 14% of matures, and only 14% of the matures read ebooks. They don't like ebooks. All right, and so I get 21%. Okay, just the probability of who reads ebooks. Now it says, suppose the person reads more ebooks than print books. What's the probability that she or he is a millennial? So this is what it always builds to, is one of these given statements. Not always, but a lot of times, okay? So what this is saying is that they like ebooks better. That goes second. We know they're into ebooks, okay? What's the probability they're a millennial? And so I'm going to set up my formula, which is on your sheet, millennial and ebook, divided by the probability of ebook. In the top, we're multiplying millennial and ebook together because we have the conditional. So I'm going to do 0.34 times 0.2. All right, millennial and ebook. And in the bottom, what am I going to put, you guys? The answer I just got from part B. This would be all your pathways to ebook. All right, and when I divide those out, I get 32% chance that if they like ebooks, they're a millennial. All right, last one. Many women choose to have annual mammograms to screen for breast cancer after age 40. A mammogram isn't foul-proof. Sometimes the test suggests that a woman has breast cancer when she really doesn't. This is called a false positive. Other times the test says that a woman doesn't have breast cancer when actually she does. That is a false negative. Suppose we know the following information about breast cancer and mammograms in a particular region. 1% of women over age 40 have breast cancer in this region. For women who have breast cancer, the probability of a negative mammogram is 0.03 or 3%. For women who don't have breast cancer, the probability of a positive mammogram is 6%. A randomly selected woman age 40 or over from this region tests positive. What's the probability she actually has breast cancer? So we're going to first make a tree diagram. Okay, what do you think goes first? Has it or doesn't have it? That is correct. She either has breast cancer or does not have breast cancer. Okay. What percent of women in this region have it? 1%. So I'm going to put 0.01 here and 0.99 here. All right. Now, what do you think goes on the next? What's conditional here? Yeah, just getting a positive or a negative test, okay? So I have positive, negative, okay? They either have it and get a positive and negative test, or they don't have it and get a positive or a negative test. So this one says, for women who have breast cancer, the probability of a negative mammogram is 0.03. So they have it, but they got a negative mammogram. They should have gotten a positive, but 3% still got a negative. So then what percent got a positive? Okay, as they should, all right? And then for women who don't have it, 6% of those got a positive reading. They shouldn't have, right? But 6% got a positive reading, which means that 94% got a negative. Okay, now let's answer the question. Find the probability that she actually has it. So she tested positive. What's the probability she actually has it? So we're setting up our conditional statement. What do we know happened? Yes, we know she got a positive test result. What are we trying to find? If she actually has it. What's the probability she actually has it? So we need has it and test positive over the probability of testing positive. What goes in the top? What am I going to multiply? Yeah, I'm going to multiply 0.01 times 0.97. So that's the chance she has it and tests positive. In the denominator, be careful because there was no part B to just fill in, right? This is all the pathways to positive. There are 2 ways to test positive. What we just did, right? She could have it and test positive, or what else? Not have it and test positive, which is 0.99 times 0.06. Both of those pathways have to go in the bottom. All right, those don't cancel because of that lovely plus sign, and then make sure you actually plug it in, get an answer, and it is 14%, which is kind of interesting to me. Okay, so what this is saying is, given she has a positive test, it's only a 14% chance she actually has it. Strange. I mean, I guess that would give you some hope. All right, let's try this worksheet.